Hello everyone. This video would focus on addition and subtraction of radicals, and this is the second part. Please feel free to check out the description box below for the link of the other series of topics that are related to radical expressions. Now let's have the parts and definition of radical expressions. Please remember that these are the parts of every radical expression. The first part is the radical symbol. The reason why this is called radical expression is because it is an expression that contains the radical symbol. Our A here is called a coefficient. A coefficient is a number multiplied to the radical expression. And the letter N here is called the index. This tells you which root you're looking for. Please remember that if the value of the index is not written in there, it means that that invisible number is 2. We also have a letter C, and this letter C is named as the radicand. A radicand is the value that you are taking the root of. So this expression that we have here is read as A times the nth root of C. So this is read as square root of 36. So if we wanted to know what is the value of square root of 36, we can go ahead and equal this whole expression to x. So this is read as square root of 36 equals x. Now we are going to rewrite this into its equivalent exponential form. This expression or this equation that we have here means that x squared is equal to 36. What is x? So if you notice, our x here becomes the base of the exponential form, while our index of 2, which is invisible, becomes the exponent in the exponential form, and our radicand, which is 36, will become the answer to the exponential expression. What we're trying to do right now is we're supposed to determine the value of x such that when we multiply this x by itself twice, it will give us 36. Meaning if we have blank times blank equals 36, and it should be the same number. So then these two numbers would be 6 times 6. So 6 times 6 is 36. And so we can go ahead and rewrite this as 6 squared equals 36. And so this tells us that our x is 6. So then this square root of 36 then will equal to 6. So that's how we evaluate radical expression. So these are the parts and definition of radical expressions. Okay, before going further, let's have the definition of like and unlike radicals, since we need this in adding and subtracting radical expressions. We remember that if we say like radicals, these are radicals that have the same indices and the same radicand. While on the other hand, if we say unlike radicals, these are radicals that differ in either the radicand or the index. So let's take these general radical expressions. So these two radical expressions that we have here are like radicals. So the only two parts of the radicals that we look at to determine if it's like or unlike radicals are again the two indices or the indices and the radicands. So in this case right here, both indices are the same and both radicands are the same. It doesn't matter if the coefficients are not the same as long as the indices and the radicands are the same, then we go ahead and say that the radicals are like radicals. Now let's have the first example. So we are given 4 times cube root of 5 and negative 7 times cube root of 5. Again, the only parts that we need to check are the indices and the radicand. So in this case right here, both indices are 3, so we're good. And both radicands are 5, so we're good. We can go ahead and say that these two expressions are like radicals. Now let's take the next example. So looking at this example, we have a 3 and we have an invisible 2 as the indices. So we can say that the two indices 3 and 2 are not the same, so that we can go ahead and say that this is unlike radicals. We also have 5 and 7 as radicands, and they're not the same, so it further verifies that these two are unlike radicals. Now let's move on to the next one. Now, both of them are 7, but the other one is the whole number, while the other one has a square root on it. So then we can go ahead and say that these two are unlike radicals. So that is how we determine whether the two radical expressions are like radicals or unlike radicals. Okay, so let's go over the problem here. So we're given negative 5 square root of 8 plus 3 square root of 2. The major important reminder that we have to tell ourselves when we add or subtract radicals is that we can only add or subtract like radicals. In this case here, we have an 8 and a 2, so their radicands are not the same, although their index are the same, but the radicands are not. However, this square root of 8 can still be simplified. So I'm going to go ahead and show the work down here. I will simplify this 5 square root of 8. We can do that by breaking this 8 into its factors using the perfect squares. I will put the list of the perfect squares on the side for your guide so that we can go ahead and say that we can break this as negative 5 square root of, if we break this to its perfect square, we actually have 4. 4 is a perfect square times 2. And so this comes out 5 square root of 4 times square root of 2. So then we go ahead and say 5 square root of 4 is 2 times square root of 2. So this comes out 10 square root of 2, which is negative. So then we can go ahead and write it up here. So instead of writing this is the one that we write. So this is negative 10 square root of 2. That is equivalent to negative 5 square root of 8. Plus, we have the second one right here, 3 square root of 2. Now, notice that their indices are the same and their radicands are the same, so that we can go ahead and add their coefficients. So this comes out, we have negative 10 plus 3 is negative 7. We copy the square root of 2, and this is the sum of these two radical expressions that we have up there. Now let's move on to the next example. At this time, I would encourage you to pause this video and try this problem out on your own. And when you're done, unpause it and check your answer. Okay, so we go over the problem here. Again, we cannot add all these three expressions that we have here since their radicands are not the same. So we have 48, 27, and 7. However, we can factor this out further, this square root of 48 and this square root of 27 using the perfect square numbers, so that I go ahead and show the work down here. Okay, so what I did here was I factor the 48 out using the perfect square. I have placed the list of the perfect square on the side for your reference. So 16 times 3 is 48, and 16 is a perfect square. And so square root of 16 is 4, and that's how we got this. The same thing for 27, that's 9 and 3. 9 is a perfect square. So I go ahead and write these three expressions down here and simplify it. If you notice, only these two are like radicals because they have the same indices and they have the same radicand. This one is different. So I go ahead and add these two together and keep this. So this expression will come out. That's going to be 12 plus 6 is 18. Then we copy the square root of 3 minus 5 square root of 7. So this is the answer to this expression that we have up there. Did you get the same answers as this? Good. Perfect. Now let's move on to the next example. Okay, if you notice, their indices are the same, however, but their radicands are not the same. So we cannot combine them together out front. So what are we going to do is we are going to factor out 40 using the perfect cube. I will put the list of all the first 5 perfect cubes on the side for your reference. And then we will also do the same thing for 135. So I will show the work down here. So this one would come out, that's gonna be 4 times the cube root of, in this case right here, I am going to use the factors of 40 that has a cube root in it is 8 times 5. So 8 times 5 is 40. And so I break this down, that would be 4 cube root of 8 times the cube root of 5. So I get 4 times the cube root of 8 is 2 times the cube root of 5 is just the cube root of 5. So I keep that. So this comes out 8 cube root of 5. So this is the simplified version of this expression that we have right here. So we also do the same thing for 7 cube root of 135. So that would be, again, we are going to look for a factor of 135 such that it's a perfect cube. So in this case right here, we write 7 times the cube root of 135 can be broken down into 27 times 5, and that's 135. So 27 times 5. So 27 is a perfect cube. So we write 7 times the cube root of 27, and then times the cube root of 5. So 7 times the cube root of 27 is 3 times the cube root of 5. 7 times 3 is 21, and then that's the cube root of 5. And so I go ahead and rewrite this as, that's the first one. So instead of writing this, we got 8, and then that's the cube root of 5 minus 21, and then that's the cube root of 5. And so we can see that their indices are the same and their radicands are the same. So that we can go ahead and simplify this further. This will come out 8 minus 21 is negative 13. And we copy the cube root of 5. And so this is the difference between these two expressions that we have up there. Now let's move on to the next example. At this time, I would encourage you to pause this video and try this problem out on your own. And when you're done, unpause it and check your answer. Okay, so we go over the problem here. If you look at this problem, all of them have the same indices of 3 and their radicands are not the same. So we need to factor them out using the perfect cube. So we factor out 81, we factor out 24. Using one of the perfect cube, so that I go ahead and show the work down here. So 81 can be factored out into 27 times 3, and 27 is one of the perfect cubes, and so that is equal to 3, and we come up with this. And 24 can be broken down into 8 times 3, which is 8 is one of the perfect cubes. And so we go ahead and simplify this as negative 10 cube root of 3. So I go ahead and write this up here. And so if you notice, all of them have already the same indices of 3 and their radicands are 3. And so we can go ahead and simplify this further. That is 39 minus 10 is 29 plus 4 is 33. And we copy their radical expression. That's cube root of 3. So this is the simplified version of this expression that we have up there. Did you get the same answer as this? Good. Perfect. If you found this video helpful, hit like and subscribe for more math videos. See ya!